A warm good morning to all. On behalf of our management, our principal sir, and Department of Mechanical Engineering, I welcome all the participants to this webinar. In this session, I have to discuss about the topic developing mathematical model for solar thermal systems. I am Madheshwaran, working as an assistant professor in Mechanical Engineering Department, Jansen's Institute of Technology, Coimbatore. In this session, I have to discuss about the need for solar thermal energy. Then we move on to solar heating for industrial processing, that is ship system. Then I have to explain about what are all the challenges we are facing in ship system. Further, we move on to what is meant for mathematical modeling. Then how to develop the mathematical modeling for various solar thermal energy conversion systems like solar air heaters, solar water heaters, and solar desalination systems. So in the first 15 minutes of the presentation, I have to discuss about the need for solar thermal energy, ship system and its challenges. Then the next 35 minutes, I have to discuss about the mathematical modeling procedure, then how to develop the mathematical modeling for solar air heaters, water heaters and desalination system. I start my presentation with the question, that is, what is the need for solar thermal energy? To answer this question, go through this figure. So this figure shows the world energy consumption pattern. As per the statistics, 32% of energy is consumed by the industrial sector, 31% of energy is consumed by the transport sector, 24% of energy is consumed by residential, and 13% of energy is consumed by the others. Among this 32% of energy consumed by the industrial sector, 74% of energy is required in the form of heat, 26% of energy is required in the form of electricity. The heat energy is produced 45% by coal, 30% by natural gas, 15% by oil, 9% by renewable and 1% by others. The 74% of heat, that is equal to 85 exajoules. So the 85 exajoules is utilized here by 30% for low temperature applications, that is below 150 degrees Celsius. 22% of heat is utilized for medium temperature applications, that is 150 to 400 degrees Celsius applications. Then 48% of heat is utilized for high temperature applications, that is above 400 degrees Celsius. So from the statistics, what we are concluded here means the energy, the most of the energy that is required in the industries are in the form of heat. So the solar thermal energy converting devices have convert the available solar radiation into useful form of heat. Then the heat energy is utilized for various industrial heating process. That's why solar thermal energy converting devices gets its importance. On the other hand, the developing and developed countries are bothering about greenhouse gas emissions. The International Solar Energy Society and International Renewable Energy agencies want to reduce the greenhouse gas emissions from 30,000 metric tons of CO2 equivalent to zero within the year of 2050. So to attain this task, they carried out various technical and economical feasibility analysis and concluded that if the energy is produced 100% by renewable energy sources within the year of 2050 means, then the greenhouse gas emissions are reduced to zero before 2050. Further, they reported that the contribution of each renewable energy sources, as per their report, solar will produce 69% of required energy, wind energy contribution is 18%, biomass by 6%, hydro by 3%, geothermal by 2%. So from the last two slides, what we are concluded here means the major source of energy that is required in the industries is in the form of heat. So solar thermal converting technology can able to produce those heat. Further, if we want to reduce the greenhouse gases to zero level means, again the solar energy conversion technology contributes more. That's why solar energy conversion technology is much important when compared with all other renewable energy technologies. Now we move on to solar heating for industrial processing, that is ship system. So what is ship system means? Designing solar thermal energy converting devices particularly utilized for industrial processing. So the ship system contains array of collectors. the collectors receives the heat from solar radiation and heat the working fluids like water, air and steam, and produce hot air or hot water or steam. These working fluids are utilized for various industrial heating processes. Further, the heat can be stored in the heat storage device. It can be utilized at night time or low sunshine hours. At present scenario, more than 500 industrial manufacturers are using SIP system for their industrial processing. The installed capacity is almost equal to 4 lakhs meter square and the energy production rate is 280 megawatts of thermal energy. Now I want to show some case studies which are actually implemented in the industries by using SIP system. First one, the SIP system used in drying applications. So what is drying? Removal of moisture is called drying. So to removal of moisture, we are in need of hot air. So SIP system can produce the hot air with the maximum temperature of 120 degrees Celsius. So here TI cycles Chennai, TVS motors at Hosur, tractor and farm equipments are using SIP system for producing the hot air and drying their products in their painting booths. So TI cycle saves the energy of 56 liters of kerosene oil per day. TVS motor saves 64 kilogram of liquid petroleum gas per day. TAFE Access Limited saves 38 liters of furnace oil. Further, TTK Industries used SIP system especially for preheating the rubber. Golden Hills Tea Factory utilizing the hot air production especially for preheating and drying of tea leaves. AMR Industries utilize it for dal drying process and saves the energy. So in this industries, SIP systems are utilized to drying the products within the operation of 120 degrees Celsius. That is, it is utilized for low temperature applications. Nowadays, SIP systems are utilized in mining industries. So nowadays we are using lot of electronic components. All the electronic components are requires batteries and wires. So if you want to manufacture batteries and wires, we are in need of copper, chromium and lithium. Okay. So if you want to extract these minerals from mining industries, means we are in need of the process, that is separation process, cleaning process and drying process. So these processes are requires hot water with a temperature of 150 degrees Celsius. So with the help of solar water heaters, we are producing the hot water and carry out these processes and extracting the minerals. So in these industries we are using SIP system. For an example, Gabe Mining Company extracting copper. It is located at Sili. They use flat plate collectors with the area of 39,300 meters square. The annual energy production is equal to 54,000 megawatts of thermal energy. With the help of this solar flat plate collectors, they saved 80% of fossil fuels and they are reducing the carbon dioxide equivalent emission about 15,000 tons per year. So look at this area. The area is 39,300. It is approximately equal to 7 to 10 football grounds. So this is the one of the largest SIP system utilized for mining industry. Now I show another example, that is Centilla Mining Company. It is also located at Sili. They use parabolic trough collector for producing the hot water. The area of the collector is about 16,742 meters square. With the help of these collectors, they produce the annual energy production of 24,845 megawatts of thermal energy. Their fuel savings is about 55%. They reduce the carbon dioxide emission about 7,951 tons of carbon dioxide emissions. Right? So further, nowadays the pharmaceutical industry is also using SIP system. Here I show one example, Ram Pharma project. It is located at Jordan. They use personal collectors for their SIP system. The installed capacity of the SIP system is about 550 meters square. Then the thermal power they produce is equal to 222 kilowatts of thermal energy. They produce, the working fluid is here is steam with a temperature of 210 degrees Celsius. Further, they save the fuel about 42%. So These are all the some few case studies in actual industries where we are implementing the solar heating for industrial processing systems. Now I move on to the current position of ship systems. So around the world there are 40% of ship plants are utilized for food and beverage industries, 12% of ship system is utilized for machinery industries, 10% of plants are utilized for textile industries. Further, as per International Renewable Energy Agency's report, the installed capacity at the year of 2016 is 4 lakhs meter square. It is to be enhanced in the year of 2030 is about 1300 millions of meter square. So there is an enormous growth to be happened in this industry. So it creates lot of job opportunities for the engineers. Now I want to explain the advantages of the solar energy technology. So solar energy technology can convert into heat energy with the help of solar collectors. Further, it can be converted into electricity with the help of photovoltaic cells. Further, the solar energy is the most reliable source of energy. Why? Because it is available for millions of years. Then it not requires any transportation cost. There is no taxation. Further, it is not affected by geopolitical crisis. Then, so now the contribution of renewable energy in all the sector is about 23.7%. So in industrial sector, residential sector, transport sector and other sectors, the contribution of renewable energy is about 23.7%. It includes the electricity generation by hydropower. But the contribution of renewable energy in industrial process heating is only about 9%. In this 9%, the contribution of solar energy in industrial process heating is only about 0.001%. So look at the value, it is very, very low. I already showed that among the world energy consumption, 85 exajoules of heat is utilized for industrial process heating. But at that energy consumption, the energy produced by solar energy technology is only about 0.001%. I also showed some of the case studies, but throughout the world, only 500 to 600 companies are only using a ship system. Most of the companies not utilizing those things. So why the companies are not utilizing the solar thermal energy technology means there are certain challenges are there. Those things we have to discuss further. So what are all the challenges? First challenge is low awareness. So most of the companies not know the capability of the solar energy technology, solar thermal energy technology. Further, the companies and the practicing engineers have a confidence only in long-term proven technology. For an example, if the company is in need of a steam with a temperature of 210 degrees Celsius with a pressure of 13 bar, they are go and simply purchasing a boiler. They are not trying with solar thermal energy technology. Why people are always go with already proven technology? Then the third important drawback is system cost. The solar energy conversion technology have higher initial cost. Then there is a lag of technology. Still the solar technology have some drawbacks. So what are all the limitations in the solar thermal technology means it have a lower thermal efficiency. The system efficiency nearly ranges from 40 to 60%. Further, it can be reduced during load fluctuations. Further, the solar fraction ranges from 30 to 50%, and it also requires huge space. Further, it is affected by the climatic conditions during rainy season and during low solar radiation available conditions. The output gets decreased. So these are all the drawbacks and limitations in this technology. Further, there is a lag of suitable planning and guidelines and tools. So these planning guidelines and tools are not well established for designing solar thermal technologies. Further, lag of education and training. So to avoid these drawbacks, nowadays researchers, industrial people and academicians are doing lot of research in this area. Further, the Department of Science and Technology provides separate funding for developing solar thermal technology. So when we doing an research, then only the mathematical modeling comes into picture and play a vital role. So now we move on to mathematical modeling, that is how to develop a mathematical model for solar thermal energy converting devices. So first we have to discuss about what is mean for mathematical modeling. So all the engineering problems and the engineering system working based on some fundamental physics. If those fundamental physics are written in the form of equation, so that is called governing equation or mathematical model. So then the governing equation is solved with respect to set of boundary condition and initial condition, we will get the solution. So this is the procedure for mathematical modeling. Now I want to explain the modeling cycle. So we have a real situation. So with the help of set of assumptions, we have to convert this real situation into real world model. Why means we are not able to analyze the actual system in realistic world. So we want to simplify it. So for that purpose, with the help of set of assumptions, it is converted into real world model. Then based on the certain fundamental physics and the mathematical basics, we will convert the real world model into mathematical model. After converting into mathematical model, with the help of certain mathematical procedures, that is finite, it may be finite element method, finite volume method, or finite difference method, we solve this mathematical model and get the results. After getting the results, we are analyzing the results and do further validation. So this is called the modeling cycle. Now I move on to how to develop the mathematical model for solar air heater, right? So what is solar air heater? Solar air heater is a device which extracts the heat from solar radiation. Then the observed solar radiation is utilized for producing the hot air. So that is called solar air heater. So the in this figure shows the simple solar air heater which are used in the industries. The simple flat plate solar air heater consists glass cover, then observer plate, back plate, and the insulation. So how the system works? When the solar radiation strikes on the observer plate through this glass cover, the observer plate gets heated. So when the air flows below the observer plate in the airflow channel, means due to the convective heat transfer, the heat is transferred from observer plate to this air and the air get heated. So this is the simplified working principle of ordinary simple flat plate collector. Now a researcher want to enhancing the efficiency of the system. Why means the normal efficiency of the system is ranges from 35 to 45%. Now if you want to enhancing the efficiency of the system, means we have to do certain design modification. So as a researcher, he implementing a small design modification in this system. So what is the design modification means? They inserting one jet plate in between the observer plate and the back plate in the airflow channel. So this is called the jet plate. So what is mean for jet plate means the plate with lot of smaller holes. The holes diameter may be 5 mm. So what is the influence created if you inserting a jet plate means in conventional air heater, the air is flowing which is parallel to the observer plate and extracting the heat. But during this condition, the convective heat transfer coefficient is low between observer plate and air. That's why the efficiency is low. But if you inserting a jet plate in the modified system, what happens? When the air entering into the airflow path, due to these holes, the airflow direction is get changed and it moves perpendicular to the observer plate and make an impingement on the observer plate. So the convective heat transfer coefficient is increased and the heat transfer also increased. So now I want to know what is the influence of the new system on the efficiency of the system and what is the output temperature of the new system. So and also I want to know what is the optimum dimension between the jets, that is pitch, that is streamwise pitch between two adjacent jets. So these things we have to analyze before go to the experimental analysis. So for that purpose we are carried out the mathematical modeling. So what is the first step in mathematical modeling? We have to do certain assumptions. Then only the complicated actual system is modified into simple system for carried out the mathematical analysis. So what are all the assumptions we are carried out here? The solar air heater operates at under steady state condition with one-dimensional heat flow. So this means in actual condition the system operates at under unsteady state mode, but here it operates at steady state condition. In actual condition it is a three-dimensional flow. For sake of simplicity we are considering one-dimensional flow. Then the temperature drop through the glass cover, observer plate, jet plate and back plates are negligible. So we are considering all these along the length of all the collector components are in equal temperature. Further, the heat transfer coefficient also equal at all the points of the collector components. Further, there is no air leakage in the system. So in the actual system we have an air leakage, but we are assuming in the theoretical modeling there is no air leakage is available. So with these assumptions we have to develop the mathematical model. So look at this collector. It consists 6 components, that is a glass cover, observer plate, then upper airflow path, then jet plate, lower airflow path, back plate and thermal insulation. So if we developed the energy balance equation for all these systems, then the mathematical model has been completed. So now we have to develop the energy balance equation for each component. The first component is glass cover. So what is the fundamental physics behind this? Energy into the cover is equal to energy out of the cover, right? Now what is the energy into the cover? The glass cover gets the energy from 2 ways. One is from the sun, from the solar radiation. The another way is if you compare the temperature of the observer plate and the glass cover, the observer plate temperature is high. So due to convective heat transfer and radiation heat transfer, the glass cover gets the energy from the observer plate. So those things are written in the left hand side of the equation. So alpha G into S, that is the energy given by the solar radiation. Here alpha G is called observability of the glass cover, S is called solar radiation. So if you multiply these two parameters, this much amount of energy is given by the solar radiation. Then how much amount of energy is transferred from observer plate to glass cover by convection mode of heat transfer? Means Hc represents convection mode of heat transfer, P and C represents plate to cover into Tp minus Tc, that is the temperature difference between plate, observer plate and cover. So this is based on the convective heat transfer equation, that is Newton's law of cooling. Further, what is the amount of energy received by the glass cover from the observer plate by radiation mode of heat transfer? Means HR will represent radiation mode of heat transfer between plate and cover, and the temperature difference we have to write Tp minus Tc. So the left hand side of the equation will represent the energy into the glass cover, that is equal to energy out of the glass cover, that is represented by the equation shown here. So here how the heat is lost from the glass cover means the wind is blows over the solar air heater. So some of the heat is go through the ambient by convective heat transfer through to the wind. So that is given by HW into Tc minus Ta. HW is shows the convective heat transfer coefficient between wind and glass cover. Tc is the glass cover temperature, Ta is the ambient temperature. Further, some amount of heat is radiated to ambient, so that is given by HRCS into Tc minus Ts. So this is equation 1. Here we are write the energy balance equation for glass cover. Now we move on to write the energy balance equation for the observer plate. So how the energy the observer plate gets its energy? The glass cover is a transparent glass cover. So when the solar radiation strikes here means it passes through the glass cover and strikes the observer plate. So the observer plate receives its energy from the sun. So how to calculate that value means alpha P into tau G into S. S will represent solar radiation, tau G is the transmissivity value of the glass cover, and alpha P will represent the observability of the observer plate. So if you multiply these three parameters, that is energy into the observer plate. Further, what happens? The observed energy is transferred to the glass cover by convective and radiation mode, that is represented here. It is already explained in the previous slide. Then the remaining heat in the observer plate is taken by the air which is flows on the upper airflow path. So that is given by this term, that is HC, convective heat transfer between plate and A2, that is air available at the upper airflow path. Then the temperature difference, we have to put the temperature difference, that is Tp minus Ta2, right? Then some amount of heat available in the observer plate is go to the jet plate by radiation mode of heat transfer. So that is given by HR will represents radiation mode of heat transfer from plate to the jet plate. This is Tp minus Tj will represents the temperature difference between plate and jet plate. So this is the energy balance equation for the observer plate is over. So here the net energy collected by the observer plate is equal to the energy out of the observer plate. So this is the second equation. Now we move on to third equation, that is the energy balance equation for the air flow above the jet plate or the air available at the upper airflow path. So how the air gets heated here means it gets heat from observer plate by convective mode of heat transfer, and also it gets heat from jet plate by convective mode of heat transfer. So those things are written here. So HCPA2 into Tp minus Ta2 will represent the convective heat transfer from jet plate. HCJA2 into Tj minus Ta2 will represent the convective heat transfer from the jet plate. If you sum these two parameters, this is equal to this much amount of energy is supplied to the air. The air takes that heat and goes as a hot air to the outlet. So that is represented by QU2. So this is third equation. Now we move on to fourth equation, that is energy balance for jet plate. So here energy into the jet plate is equal to energy out of the jet plate. So how to write the energy into the jet plate means how the jet plate get energized means by the radiation mode of heat transfer from the observer plate. So that can be written as HRPJ into Tp minus Tj. So this much amount of energy supplied by the observer plate to the jet plate as shown here. Then how the energy is released here means some of the energy is given to the air that is flowing on the upper airflow path by convective mode of heat transfer. Some amount of heat is released to lower airflow path by convective mode of heat transfer. The remaining heat available in the jet plate go to the back plate by radiation mode of heat transfer. So that is shown in these three terms. That is HCJA1 into Tj minus T1 will represent convective heat transfer from jet plate to the airflow path at the lower airflow channel. HCJA2 into Tj minus Ta2 will represent the convective heat transfer from jet plate to the airflow at the upper airflow path. Then HRJBP will represent the radiation mode of heat transfer from the jet plate to back plate by radiation mode of heat transfer. So this is the fourth equation. Now we move on to fifth equation, that is the energy balance equation for the air which is flows on the lower airflow path. So the energy into the air, that is equal to energy out. So how to write this equation means the air receives the heat or energy from the jet plate and observer plate by convective mode of heat transfer. So that is given by these two terms. So that is equal to the energy taken by the air in the lower airflow path. So HCJA1 into Tj minus Ta1 will represent the heat energy given to the air by the jet plate. HCBPA1 into TBP into Ta1 represents the energy given by the back plate to the air which is flowing on the lower airflow path. So if you add these two parameters, that is equal to the energy taken by the air in the lower airflow path. So this is equation number 5. Now we move on to equation number 6, that is energy balance equation for back plate. So how the back plate is get the energy or heat means by the radiation heat transfer from the jet plate. So that is represented by HR, that is radiation heat transfer coefficient between jet plate and back plate into the temperature difference between both the plates, that is Tj minus Tbp. Then how the energy get released or energy goes out means some amount of energy is transferred to the air by convective mode of heat transfer, that is shown here, and also it is explained in the previous slide. Then the remaining energy in the back plate go to the ambient as heat loss. So that is given by UB into TB minus TA. So this is the energy balance equation for back plate. So this is the sixth equation, right? So now we write the energy balance equation for all the 6 components in the jet impingement solar heater. So now we have to solve this equation and find the temperature of each component. Then only we can able to find the outlet temperature and the efficiency of the system. So all the 6 equations now written in the form of matrix. Okay, the matrix vector. So here Tc will represent temperature of the cover, Tp will represent the temperature of the plate, Ta2 will represent the average air temperature in the upper airflow path, Tj will represent the temperature of the jet plate, Ta1 will represent the temperature of the air at lower airflow path, Tbb, that is temperature of the back plate. So if you solve this equation, there are many methodologies are there. I am here using matrix inversion technique. If you find all the temperatures, then we can able to find the efficiency of the system. So to solve this equation, we are in need of this convective heat transfer coefficients. So how to know this convective heat transfer coefficient means, so the convective heat transfer coefficients are listed here. Some of the convective heat transfer coefficients are basics from, we take it from heat transfer subject. The remaining things are taken from the previous studies from the previous researchers. Then if you substitute all these things, we can find the temperature. After finding the temperature, we are calculating the efficiency. After calculating the efficiency, we have to validate our results. Here the red dotted line will represent the present analytical model results. Then black solid line and this blue dotted line will represent the results by previous researchers. So I compare my analytical results with the previous researchers' result. There is a maximum deviation of my result is about 8%. So it gives better validation. So in that way we have to validate our result. Further, the first law efficiency for my present system, the modified system, is about the maximum of 60% at the reduced temperature parameter of 0. So it is much higher than the conventional solar heater. The conventional solar heater is nearly about 35 to 45%. Here it is increased up to 60%. So the system will give maximum efficiency and better performance. Further, I have to find what is the optimum pitch distance between two adjacent jets. So the x distance is varied between the jets. So from the results, it is concluded that if x by dh value is 0.435, it gives the maximum efficiency up to the temperature rise parameter of 0.055. So from the analytical studies, before go to the actual experimentation, I know how much percentage of efficiency is enhanced by the modified system when compared with conventional solar heater, and also I can able to optimize the dimension of the pitches. So this is the major advantage of mathematical model. Now I hope you understand about the concept of developing mathematical model for solar air heaters. Now I move on to the mathematical model for solar water heater applications. So what is solar water heater? So solar water heater is a device which observes the energy from solar radiation. Then the observed energy is utilized for producing hot water. So the system consists a lower header and upper header. These two headers are connected by the riser tubes. Then the header assembly is assembled over the observer plate. Then the observer plate is connected by a enclosure with well insulated for avoiding the heat loss. The top of the enclosure is covered with a glass cover. So when the solar radiation falls over the observer plate through the glass sheet, the observer plate is get heated. Then the heat is transferred to the water which is flowing in the riser pipe. Further, the solar water heater system is classified into two types. One is natural circulation, another one is forced circulation. So what is the difference here means, if the water flows from lower header to upper header, due to density difference, due to the buoyancy forces, it is called natural circulation solar water heater. If with the help of a pump it is circulated, means that is called forced circulation water heater. Nowadays we are using both the systems. In household applications we are using natural circulation. In for company purpose, the industrial purpose, we are using forced circulation system. Further, the efficiency of the solar water heater at forced circulation may be the maximum of 60% at tested operating conditions. So to enhancing the efficiencies, nowadays solar water heaters is incorporated with nanofluids. So what is nanofluid means? We are adding some nanoparticles with the water. So we are preparing the nanofluids. So how the system works means, here the solar collector is filled with nanofluid. So it absorbs the radiation, then the nanofluid gets heated. Then the heated nanofluid is sent to the tank. In the tank we have one more heat exchanger. So the heated nanofluid go through this heat exchanger and heat the water which is stored in the tank. After heat transfer, again the nanofluid comes to the solar water heater, so that is solar collector, for again it extracts the heat from the solar energy. This cycle is repeated for heating the water further. So this is the actual experimentation setup. Now we want to develop the mathematical model for this solar water heater. So why we want to develop the solar water heater means, when we are using nanofluid, which type of nanofluid we have to use for getting the maximum efficiency, what is the fraction of nanomaterials to be added for to get the better efficiency, these things to be analyzed. So for the purpose we are developing mathematical model. So to developing the mathematical model, we have to do certain assumptions. Again, the steady state condition, there is negligible heat capacity in the solar water heater components. Again, it is a one-dimensional analysis. Then the properties of nanofluids are varying linearly. Then there is no temperature gradients across the components of the solar water heater. So with these assumptions, I convert the actual real system into simplified system. Now we move on to mathematical model. So this is the simplified diagram of solar water heater, that is a cross-sectional view. So it gets the energy from the sun, then the working fluid gets heated. So how to write the energy balance equation here means, here GT represents the amount of energy that is received from the sun. Then UL into TP minus TA will represent the energy losses from the collector. So energy in minus energy loss, that will gives the useful heat energy gained by the working fluid. Okay. So QU is equal to, here AC will represent the area of the collector. That is common for both the parameters. So we will take it as outside. Right. Now the solar radiation is a known parameter. Then TA also, TA here represents temperature of the ambient. So that is also known parameter. Right. So here UL we have to calculate. Right. So here TP is an unknown parameter. For initial calculation you have to assume certain value. That's it. So now how to find UL? What is UL? It is the overall heat transfer coefficient value. So what are all the loss coefficient contributes here means UT. UT represents top heat loss coefficient. UB represents bottom heat loss coefficient. UE represents edgy heat loss coefficient. So how to calculate those heat loss coefficient here means with the help of this formula. Here sigma will represent Stephen-Boltzmann constant. TP is assumed plate temperature, that is observable plate temperature. TA is the ambient temperature. Further, Ng will represent number of glass covers. C is a constant. It is based on the tilt angle of the solar collector. Then tau is the transmissivity of the glass cover. Epsilon P is the emissivity of observable plate. Epsilon G is the emissivity of glass cover. So with the help of this formula we can find the top heat loss. Then the bottom heat loss is calculated using this formula. Here TB will represent the thickness of the insulation. KB will represent the thermal conductivity of the insulation. HBA will represent the heat transfer coefficient between the collector and ambient. In the same way, UE is the edge loss coefficient that is calculated using this formula. This is edge thickness. This is the thermal insulation, thermal conductivity of the insulation. This will represent, HEA will represent heat transfer coefficient between the edge and the ambient air. So with the help of UE, UB and UT, if you find these three parameters, we will find out overall heat loss coefficient. So if you substitute the value of UL here, we know what is the useful heat energy gained by the working fluid which is used in the solar water heater, right? But during this calculation, the TP is assumed value. So far we are not known the accurate value. Okay, so in the next step we have to find the temperature of the plate. So how to find the temperature of the plate? Using this equation. Here QU, T in is the inlet temperature, AC is represents area of the collector, UL is the loss coefficient. Here QU is the useful heat gain what we calculated in the previous step. But here the unknown parameter is FR, that is heat removal coefficient. So how to find the heat removal coefficient? We have to use this formula. In this formula all the parameters are known. M is mass of water that is flowing there. Cp will represent specific heat. A is the area of the collector. All these things are known parameters except F dash. F dash is the collector efficiency factor. So how to find the collector efficiency factor? Use this formula, the third formula. So in this formula again all the parameters are known except F and HFI. That is F is called standard fin efficiency factor. So that is calculated using this formula. HFI is the convective heat transfer coefficient between the copper tube and the flowing fluid. So that is calculated using the Reynolds number. So first if you want to know H, find the Reynolds number. So the Reynolds number formula is 4 into Mr divided by pi into dA into mu nu. So Mr will represent the mass flow rate through the riser tube. Then D is the diameter of the tube. Then this is viscosity of nanofluid. So if you find the Reynolds number, if the Reynolds number is less than 2300, it will represent the flow is laminar. So you can use this formula for finding the H. Suppose the Reynolds number is greater than 2300, it will show the turbulent flow. So during that condition, using this correlation for finding the Nusselt number, then after finding the Nusselt number, using the formula of HD by K, find the heat transfer coefficient, then we can find this. So after finding F, F dash and FR, we can substitute the FR and find the TP. So this is calculated value of TP. So now you have a guessed value of TP, that is initial assumption, and calculated value of TP. Now substitute these two values of temperature of the observer plate in this equation and check whether this condition is satisfied. Whether the difference between guessed value and find out value is less than or equal to 10 to the power of minus 5 means we go for further process. Otherwise, the find out temperature of the observer plate is again substituted here for finding QU. Once again the iteration to be repeated. So in the same way the iteration is repeated. When the condition is satisfied, then we can stop the iteration. Then we will take it as that is the value of QU and that is the value of temperature of the plate. So after finding the QU value, we can find the outlet temperature of the nanofluid or the outlet temperature of the working fluid with the help of this formula. After finding the outlet temperature, we are finding the efficiency of the collector with the help of this formula. So the efficiency of the collector is now find out. So now I explained the mathematical modeling developing procedure and the calculating procedure for solar water heater. So in this graph shows I did the analysis for the solar water heater. Only the system operates with water and the system working with aluminum oxide nanofluid, and the system may be worked with cerium oxide nanofluid with 0.05% of cerium oxide as a cerium oxide concentration. So from the results what we are concluded here means when you operated only with water, the maximum efficiency is about 61.29% as shown here. Okay. Further, if you use aluminum oxide nanofluid with 0.1% of volume of aluminum, then the maximum efficiency is about 73.06% at tested condition. Further, if you use cerium oxide as a nanofluid, then the efficiency is about 81.26%, with the cerium oxide concentration is about 0.05%, right? So from this graph, further we concluded that at all the operating conditions, cerium oxide nanofluid will give better performance when compared with water and aluminum oxide based nanofluids. So in this way, we can be able to find which nanofluid will give the better efficiency and how much amount of concentration of nanoparticles to be added for gets the better performance. So these things can be find out with the help of mathematical modeling. So these are all the advantages of mathematical modeling. Now we move on to the next system, that is mathematical model for solar desalination system. So what is solar desalination system? So solar desalination is a technique to produce a water with low salt concentration from a seawater or brine solution with the help of solar radiation. So I am here using solar still for desalination purpose. So the solar still consists three important components. One is glass cover, another one is water, third one is basin liner. Now I have to explain how the system will work. When the solar radiation falls over the basin liner and water through the glass cover, so when the solar radiation is passed on the basin liner, means what happens, basin liner is exactly equal to an observer plate, so it gets heated, then the heat is transferred to the water. So what happens, the water gets evaporated, then the evaporated vapor goes and contacts with the low temperature glass cover, then it starts to condense, so we will get the purified water here. Okay, that is, we will get the fresh water. So in this way the solar desalination system will work. So I am here showing the experimental setup for solar desalination system. So to develop the mathematical model for this system, we have to do certain assumptions. So the first assumption is the level of the water in the basin is maintained at constant level, but in actual practice it is decreased during desalination process, but for sake of simplicity we are take it as at constant level. Further, the condensation occurs at the glass cover through the film type, but there are two types of condensations are there, but here we are taking only film type condensation. Further, the heat capacity of glass cover, observing material and insulation are negligible. Further, there is no vapor leakage in the still. Then the temperature gradient along the glass cover thickness and the water depth are negligible. So these are all the assumptions we are made for developing the mathematical model for solar still. Further, so there are three important components, so we have to write three energy balance equation. So the first energy balance equation is written for water mass in the solar still. So it contains the water mass gets the energy from solar radiation, that is I1. So why it is I1 means I amount of energy comes from the sun, but some amount of energy is absorbed by the glass cover, then the remaining energy is falling on the water, so that's why it is I1. Further, it gets heat from convective heat transfer from the basin liner to the water, so that is represented by QB, plus the rate of change of heat capacity in the water. Why? It gets the energy from the sun and the basin liner, so the heat capacity of the water is changes with respect to time, so we have to write those things Cw into dt by dt. Here Cw is the heat capacity of the water. Then this is the energy into the water mass. Then how the energy is released? So the water have energy, its temperature is higher than the glass cover, so what happens, there is a convective heat transfer between water to glass cover, so that is represented by QCW. How to find QCW means, that is the convective heat transfer coefficient between cover and water. AW will represent the area of water surface into the temperature difference between water and glass. Then the radiation heat transfer also takes place between water and glass cover, so that is find out with the help of the formula radiation heat transfer coefficient between water and glass cover, that is HRW into AW into temperature difference between these two things, that is TW minus TG, plus the evaporative heat loss between the water and the glass cover, that is given by evaporative heat transfer coefficient, that is HEW into AW into TW minus TG. Further, we have one more parameter I2. So what is I2 means? The water receives I1 amount of solar radiation. It observes something. Then I2 amount of solar radiation, it transmits to the basin liner. So that is the energy out. So the left hand side of the equation will represent the energy into the water mass, and the right hand side of the equation will represent energy out of the water mass. Now we move on to energy balance for glass cover. So the left hand side of the equation will represent energy into the glass cover. So it receives the energy of I amount of energy from the sun, that is solar radiation. Then it receives energy from the water by evaporation, radiation and convective mode of heat transfer. We already discussed in the previous slide, that is QEW, QRW and QCW. Then how the energy is lost from the glass cover means by radiation mode of heat transfer to the ambient, then convective heat transfer to the ambient, and it sends some amount of radiation to the water, that is I1. So QRG, that is radiation heat transfer between glass cover and the ambient, is given by HRG into AG into TG minus TA, that is the temperature difference. Then the convective mode of heat transfer is represented by HCG into AG into TG minus T. So this is the second equation, the energy balance equation for glass cover. Now we move on to the energy balance equation for basin liner. So the basin liner receives I2 amount of solar radiation. Why? I amount of solar radiation comes from the sun. Some amount of energy is absorbed by the glass cover. So I1 amount of energy is entered into the still. So it is I1 amount of energy is received by the water. Water receives some amount of radiation. So the remaining heat, that is I2 amount of heat, comes for the basin liner. So this is the energy into the basin liner. Then how the energy is released from the basin liner means QB into QBOT. That is, QB is the convective heat transfer between the basin liner to the water. So that is represented by HB, that is convective heat transfer coefficient between basin liner to water, and AB is the area of the basin, then TB minus TW. So that is the temperature difference between temperature of the basin liner to the water, right? Then QBOT. QBOT means the bottom heat loss. So bottom heat loss to the ambient. So the basin liner has some amount of energy. This energy is lost to the ambient due to the temperature difference, that is given by bottom heat loss coefficient into area of the basin liner into the temperature difference. So this is the third equation. So there are only three components. We will derive all the three energy balance equations. Now we want to solve these three equations for attaining the temperature of the glass cover, temperature of the water and the temperature of the basin liner. So first I took the first equation, that is the energy balance for water. So I took all the parameters with which contains TW into left hand side, the remaining parameters at the right hand side. If I do the rearrangement, after the rearrangement I integrate this equation by integrating by parts method, I will get this equation. So this equation contains time. If the time is at 0, we will get the initial temperature of the water. If the time is varied, if we vary the time for every 5 seconds, 10 seconds or 20 seconds or every 30 minutes, we will get the what is the temperature of the water is find out. In the similar way, if we rearrange the equation 2 and 3, then we know the glass cover temperature, the temperature of the basin liner is find out. After finding TG and TB, we can easily find QEW. What is QEW? It is the evaporative heat loss between glass cover and water. It is find out with the help of the formula. It is shown here, that is HEW into AW into TW minus TG. So we know the temperature, we know the heat transfer coefficient, we know the area. So QEW is known. Once you know QEW, then we can find out what is the mass of water yielded from the system, right? So in this way we can develop the mathematical model and we can develop the solution procedure for solar desalination system, especially for solar still. Now what is the modifications we did here means we are adding a sponge at the sides of the solar still. So if you add the sponge, what happens means the heat loss from the water is reduced. So the water temperature is higher, so the glass temperature is lower, so the delta T between these two systems are higher, so it will enhances the evaporative loss. So if the water evaporation is higher, we will get more yield. So we are using sponges on the sides of the still. So if there is no sponge in the still, it produces about 1.1 kilogram per day. The yield is 1.1 kilogram per day. If the sponge thickness is 3 mm, the yield is about 1.3. I further enhances the sponge thickness to 5 mm, the yield is increases up to 1.5 kilogram per day. But further increases in thickness may reduce the water yield. So in that way I can be able to find what is the design modification, how it enhances the output. Okay, what is the effect in the output. So these things can be analyzed by the mathematical model before we do the actual experimentation. So that's it. So in this session I explain, I create certain awareness about solar heating for industrial processing. Then I explain how to develop the mathematical modeling for various solar energy converting devices like solar water heaters, solar air heaters and solar desalination systems. Now I complete my presentation. If you have any queries, kindly post your queries to my mail ID or the ResearchGate link which is available in the description. Further, I thank all the participants for their passionate listening. Then I thank the management, our principal and the HOD sir for their continuous support. Further, I extend my thanks to Professor Vijayaraghavan and Professor Krishna Kumar for their technical support. Thank you all.